Hello and welcome to my talk titled An Agency-Directed Approach to Test Generation for Simulation-Based Autonomous Vehicle Verification. In this presentation, you will learn how agency can be used for test generation. My name is Greg Chance and I work at the University of Bristol in the Trustworthy Systems Laboratory. This research was done with my colleagues Abhinoop Gabriel and Kirsty Nieder, also from the University of Bristol, and Severin Leman and Tony Pipe from the Bristol Robotics Lab. This research aims to address some of the challenges surrounding autonomous vehicle testing, which is principally concerned with the detection of software failures and how we can gain confidence in the correctness of an autonomous system. We support the use of simulation for verification because this allows full control of the testing environment for safer and more efficient testing, which also allows biasing towards edge cases and making the rare event happen more often. Furthermore, simulation logs can be stored and replayed for auditing and evidence to regulators. So how can we effectively generate tests? And can this be automated? Furthermore, if test generation is automated, will the tests still be interesting or useful? How much testing is required for sufficient confidence is still an open research question, although some authors have proposed road testing miles based on confidence intervals around current fatality rates at around 275 million miles. Waymo have also achieved over 7 billion miles of simulated driving. This type of testing, although it may instill public confidence and allow gathering of data, actually results in very few interesting scenarios, and using this method for achieving coverage targets would be inefficient. Driving tests towards specific verification requirements may be a more efficient route to acquire sufficient confidence in the autonomous systems. We will discuss the current range of verification techniques and if the introduction of agency can assist in test generation, if this method can outperform random, and if so, at what cost. We classify the autonomous vehicle in a simulation test bench as a responder device under verification, as the autonomous vehicle responds to the environment that is presented to it, as it makes progress towards its own goal or destination, whilst maintaining legally compliant driving behaviour. We propose using agency for the verification task, which is goal-directed and targets specific verification requirements. Furthermore, leveraging inter-agent communication, sets of agents can be used for coordinated testing for finding test cases that are difficult or impossible with random techniques. The diagram to the right originated from a paper by Mark Utting and co-workers. It shows a taxonomy of model-based testing. We would propose an addition to the paradigm within the model specification of agency-based. In the test generation technology path, a node for agency also. So how do we define a good test case? In the marvellous book, Software Test Automation, Mark Fuster and Dorothy Graham propose 4 attributes of a good test case. How effective the test case is at detecting software faults, how efficiently these tests reach the verification goals and the resources used to get there, and how robust the test cases are to changes in the software, in our case, the autonomous vehicle control software interacting with the simulator. We set out to compare our new agency-directed technique against random-based techniques using these attributes. So, just some terminology in case some listeners are not aware of the terms used within the autonomous vehicle testing domain. A scene is a collection of static objects such as the road network layout, the train, and road furniture. A scenario is the temporal development of a scene, including dynamic actors within it. A situation is the subjective conditions of the actors within that scene. And an assertion in this context is a way to capture and check the vehicle behaviour against driving regulations and rules. When tests are generated, they can be executed within a test bench. In the schematic of the test bench used for testing an autonomous vehicle in simulation, the experiment is externally specified and then instantiated within the test bench, which generates the scene and the actor's input to the simulator. The VBI is an interface to the vehicle, a vehicle behaviour interface that allows multiple vehicle controllers to be connected, plugged and played into the test bench. Upon execution of the simulator, the actor dynamics are logged and the situation can be interpreted from this information, allowing useful feedback to the actor controllers. Interpreting the situation also allows assertion testing against a database of assertions, which are the rules, regulations and social norms of driving. Ideally, coverage should be collected not just on the assertions that are defined, but also on the requirements of the experiment and the code coverage of the vehicle controller, if this is accessible. Within the work presented here, we will focus on the experiment instantiation and the vehicle behaviour of the actors in the simulator only. This is represented by the red outline. With respect to test generation methods, our research considered the following options. Tests can be written manually by verification engineers. This tends to be very effective in terms of coverage and meeting verification objectives, but is expensive considering the engineering effort required. Tests can be generated using random techniques, which is usually inexpensive once the random test generation environment has been set up, but often results in tests that are not very interesting or even invalid. However, coverage can often be gained quickly using random test generation right at the start of the verification process. Accidentology can be used to drive test case generation by investigating previous human driving errors held in large accident databases. Of course, the mistakes made by humans may not be the same mistakes made by autonomous vehicles. We can also use a data-based approach where we observe real driving scenarios from sources such as traffic cameras. However, this method may result in many tests that are not interesting and hence don't add to coverage. Generation can also be driven towards edge cases where rare events are made to happen more often than they normally would. This often leads to interesting test cases. The test objective in our investigation was to exercise the collision avoidance logic of an autonomous vehicle. However, no controller was used in the code execution, but tests were generated to bring an autonomous vehicle to the point where it must make a behavioural change. Thus, our research focused on test generation, not on the outcome of the testing, i.e. not whether the AV passed or failed the test. All we were interested in was whether the test would create a situation that was likely to trigger the AV's control logic. Activation of assertion was used as the criterion to assess whether the test achieved the test objective. We illustrate the benefits of the agency-directed approach through a case study. In the experiment, we set out to generate pedestrian safety tests that follow along the lines of the Euro NCAP CPNA 25. The testing environment was comprised of a stretch of straight road with pavements on either side, and a mock autonomous vehicle drove along one lane at a fixed speed. Pedestrians were spawned at random pavement locations, although some are excluded as no successful test can be generated from these locations. These invalid locations are shown in dark grey in the middle figure. In front of the vehicle, we define an area of stopping distance where intersection with a pedestrian would result in an unavoidable collision. In front of this stopping distance, we define a precondition zone where the vehicle has sufficient time to stop or manoeuvre out of the way. If a pedestrian agent intersects this precondition zone, then we say a successful test has been generated. These zones are defined in the middle picture on the right-hand side. In the study, we repeat each of the test generation methods 1,000 times and terminate the episode when a successful test is generated, or when the autonomous vehicle exits the road to the right-hand side, which is an unsuccessful or uninteresting test case. Only successful test cases contribute towards test generation accuracy. In the animation in the lower figure, we see the leading edge of the precondition zone as a grey bar moving from left to right, and the pedestrians are yellow squares. We initially experimented with the JSON BDI environment, but ended up carrying out the tests using a Python-based grid world. In future work, we plan to use the OpenAI GIM environment. The list of test generation methods we used is shown in the table on the right-hand side. The random method moves the pedestrian in a random direction at each simulation tick, which includes taking no action. The constrained random method constrains the pedestrian to move along the pavements and randomly crosses the road with 10% probability. The proximity method is the first of the agency-directed approaches, which moves the pedestrian along the pavement and crosses the road when the vehicle is within a 15-unit radius. The election method has the same behaviour as the proximity agent, but out of a group of pedestrians, just a single one is elected to cross the road, the one that is closest to the vehicle. All the pedestrians are randomly initialised on the pavement in valid locations, and the randomisation is controlled with seeding, so the different methods generate the same initial locations. This helps promote tests that satisfy the robustness attribute mentioned previously. All methods are subject to the same performance metrics. Accuracy is defined as the total number of successful tests generated as the ratio of the total number of episodes. A successful test is one where a pedestrian is found in the precondition zone, and an unsuccessful test is where the vehicle exits the scene without triggering the precondition. A scoring system is used to penalise tests that are longer, so at one point living cost is applied to the pedestrians at each simulation tick. This is equivalent to the efficiency attribute defined previously. If the pedestrian walks into the road, they incur a 5-point penalty per tick. If the pedestrian enters the precondition zone, then a reward of 100 is given. The road penalty is given to discourage pedestrians walking in the road for long periods of time and promoting more realistic test cases. For each test generation method, we also record the CPU execution time and the test generation time, which is the time taken for a pedestrian to generate a successful test in simulation ticks. A reduction in these metrics will promote the economy attribute of good test cases mentioned previously. Let's review the results from our case study. The figure on the right-hand side shows test generation accuracy as a function of the number of agents for the random and agency-directed test generation methods. The random-based methods are the hollow markers and the filled markers are the agency-directed methods. The first thing to note is that as the number of pedestrians increases, the likelihood of generating a successful test increases due to the sheer number of actors. For this assertion, it is easier to generate successful tests when there are a lot of pedestrians, but a high number of actors is unrealistic and uneconomical and may result in test cases such as a zombie attack, where crowds of actors walk towards the vehicle. So we focus our attention on fewer pedestrian agents. Here we can see that the agency-directed approach generates 3 times more successful tests than random-based methods for a single pedestrian agent. We can also note that a single agency-directed pedestrian generates the same number of successful tests as 4 random pedestrians. Next, we present the average score with confidence intervals as a function of the number of agents. And this is an indicator of how realistic the test cases generated are. Note that we only show scores for successful tests, and the score is averaged over all the pedestrians. So as the number of pedestrian agents increases, the maximum score that can be attained drops. The graph shows the maximum theoretical score that can be attained as a green dotted line. The results show that the agency-directed method gives higher scores than the random-based approach, indicating that these generate more realistic tests. However, this approach is overly optimistic as it discounts failed test cases, which we count for in the next set of results. Here we show a combined test score and accuracy plot, which promotes scores attached to high accuracies. So this score is a measure of both successful tests and realistic test generation. Again, the agency-directed method shows a clear improvement over the random-based approaches. Now we consider the economy of our test generation approaches. We monitored the CPU time to execute pedestrian actions for each of the method types. Here, the random-based approaches excelled, and the agency-directed methods were 4 times slower to execute the agent actions. Furthermore, the election agent used 30% more resources than the proximity method. Finally, we consider the test generation time, which is how long it takes for one of the pedestrians on average to generate a successful test based on simulation ticks. We observe that the random-based techniques generally take more simulation ticks to generate a successful test than agency-directed methods. This may be important if your simulation is computationally expensive to run per tick. So even though the agency-directed methods use more CPU time to execute their actions, they are found to require fewer simulation ticks, which may be more important when used in a 3D rendered environment than a grid world. Here we present a summary of the results for 3 pedestrian types. The table shows the method type, the number of lines of code, the test generation accuracy, the CPU time to execute the agent action, the score based on the penalties and rewards as a ratio of the maximum theoretical score, and the simulation ticks taken to generate a successful test. Considering the random method as a baseline for this experiment, the agency-directed proximity approach for just a few additional lines of code significantly improves the accuracy of test generation, going from around 50 up to 85%. The proximity agent did use more CPU resources in order to execute the agent actions, but this resulted in tests being generated faster in terms of simulation ticks. The election-based approach used significantly more lines of code and did not result in as good an improvement in test generation accuracy as the proximity method. Furthermore, the CPU execution time of the election agents was greater than that of the proximity method. However, this did result in more realistic test cases, as shown by the increase in score, with the pedestrians spending less time in the road and generating shorter tests. So, in summary, the agency-directed proximity method was a real surprise, using a similar number of lines of code as the constrained random method, but with a 30% improvement in test generation accuracy. The election agent produced the most realistic tests, but I think that its potential would be better exploited in more complex scenarios. The agency-directed methods tend to use more CPU resources than the random techniques, but tend to find the test cases faster in terms of simulation ticks. So in conclusion, we have found that the agency-directed test generation is a novel, model-based technique with a high potential for simulation-based testing of autonomous vehicles. We investigated the use of agency-directed test generation for a key assertion, and using a case study, we looked at generating tests based on the Euro NCAP 25 vulnerable road user assessment. However, this methodology could be easily adapted to other assertions or scenarios. The agency-directed test generation has been shown to generate more accurate tests, generate tests that are more realistic, use slightly more CPU resources, but find effective tests faster than random test generation in terms of simulation ticks. Thank you for watching. I hope you learned about the benefits and potential of using agency for test generation. I really look forward to your questions in the session, which is at 10 a.m. UCT +1 or British Summer Time, on Tuesday, which is the first session of the conference. Please feel free to contact us on the email addresses above with any questions you have, or if you are interested in collaboration. Thank you.